Logistic regression models fall within a general family of models known as generalized linear models. Within this family of models, there are three characteristics about each model that helps distinguish or allows one to differentiate between the different kinds of models. The first component of a generalized linear model is a random component, where you specify the distribution of your response variable. For us, with a logistic regression model, y had a Bernoulli distribution to it. The second component is what's referred to as a systematic part. This simply is the linear combination of the regression parameters with the explanatory variables, what we've been referring to as the linear predictor. Lastly, there's a link component. What this does, it links this systematic component to the expected value of the random component. In other words, the expected value, let's say y. So for us, the link component was the logit link. Now, the term generalized linear model, the linear part comes about because of the linear form of these regression parameters in our model. Nonlinear models would have a situation such as this, where maybe you take x, raise it up to, let's say, the beta power. So in that setting, the beta regression parameter is in a nonlinear format. Here, since we take this linear combination, we have a linear format. Now note, in the past we've talked about how to allow, for example, a quadratic term to be in the model. Maybe you have beta 2 times x raised to the 2 power. This is still part of a generalized linear model because I have this linear combination of the betas with the x. Now the GLM function gets its name from this abbreviation of GLM for generalized linear models. There are many other types of generalized linear models in addition to a logistic regression model. All of you are familiar with one already, the normal linear regression model. This is the standard kind of model that's introduced in an introductory statistics course. In that case, y has a normal distribution to it. Here's your systematic component, and the link function, or the link that's linking the expected value of y with the linear predictor part, is just simply, you can say, the identity function, meaning, let's say, 1 times the expected value of y. In chapter 4, we're going to learn about a particular kind of generalized linear regression model known as a Poisson regression model. In that particular case, we're going to let y have a Poisson distribution to it. This is a common probability distribution that people use when one is dealing with counts. Now, you might be thinking, well, wait a second. When we were dealing with a binomial distribution, we were dealing with counts too. But in that particular case, our counts were the number of successes out of a particular number of trials. So there was a maximum possible value for y. Instead, with a Poisson situation, you don't necessarily have a maximum possible value for y. You're not observing, let's say, successes out of a particular number of trials. You're just observing the count of something. More on that in chapter 4. And then the link here is the log link function. Simply take the natural log of the expected value of y, connect it with the systematic component, the linear predictor part. Now, in chapter 2, we are referring to, or we are concentrating on binary regression models, where most of this time we've been talking about one particular type of binary regression model, a logistic regression model. Within this generalized linear model family framework, there are actually 2 other generalized linear models that are often used for binary responses. Well, let me back up a second there. I say often use, I should say often discuss. We'll talk about more later on how much they actually do get used. Now, one of these models is called a pro-bit regression model. Here's the statement of the model, and you can see that it has similarities to what we had previously for the logistic regression model. Instead of a logit link, we use a pro-bit link. What exactly is this pro-bit link? Well, to help discuss this, let's go back to something that we've seen before. Now let's say that Z has a standard normal distribution to it. I want to find the probability that Z is less than 1.96. That value is 0.975. Equivalently, we've talked about it in this context before, where we had the 0.975 quantile from a standard normal distribution is 1.96. How do I find that? I can use the Q norm for quantile normal function to find the 0.975 quantile. Conversely, one could look at the P norm function to find the probability that Z is less than 1.96, and you get 0.975. And so what this P norm function is doing is using what's called a cumulative distribution function for a standard normal. If you're not familiar with CDFs, that's okay. I'll explain it more a little bit later on. For now, you can think of this as just a way to find a probability associated with a standard normal distribution. And what we're doing is simply saying, what's the probability that Z is less than some number? Essentially, that's what a CDF gives you. Now, this pro-bit model can be re-expressed in this format here. I have pi, the probability of success, on the left side, and on the right side, I have this linear predictor inside a function. This function is the cumulative distribution function for a standard normal. In R, as in the software package, if I say P norm beta 0 plus beta 1 times x1 plus, and just what if I knew what the betas were, if I knew what the x's were, put that in there, this gives me my corresponding probability, pi. And so, let me do a little bit of erasing here. I could rewrite this function here by, let's say, using the inverse function. Note that this is the uppercase Greek letter phi. So if I use a inverse function, just like what you would learn about in algebra class, I could rewrite the model like this, where I just have that linear predictor on the right side. And now I have the inverse function right there. Well, basically, what that's equivalent to is, again, something like what we've seen up here in terms of finding probabilities, finding quantiles. So this part of our expression is what the pro-bit function does. The inverse of a standard normal CDF. Okay. The term pro-bit then, where does that come from? Pro-bit stands for probability unit. So, we're kind of working with probabilities here. We're working with units of probabilities. And so a long time ago, I believe it was in the 1930s when this model was first developed. It was actually developed before a logistic regression model. People were starting to use this kind of a model format, and a person by the name of Chester Bliss came up with the name pro-bit. And there's a kind of an interesting account of how this model came about when Chester Bliss, who was an American, but in the 1930s was in the Soviet Union at the time. Now, where does the name logit come from? Well, pro-bit regression models existed before logistic regression models, so people saw pro-bit. How about we use logit as a short way to say the log odds of a success? Now, another kind of model in the same framework is what's called a complementary log-log model. Where does the name come from? Well, take a look at how this model is written here. You have a 1 minus pi here, which is kind of like what would happen if you were to take a complement of a particular probability. So that's where the complement comes from. And then we have the natural log of the negative natural log of 1 minus pi. So there's where the log part comes from. And then I set all this equal to then that linear predictor. One could rewrite the model like this as well. In both cases, with a pro-bit model and a complementary log-log model, whatever you have on this right side, when you just have pi on the left side, you are guaranteed to always be between 0 and 1. More on that coming up. Okay, so why are these link functions used? I guess actually I was kind of getting ahead of myself. Basically, the inverse link function is chosen in a way so that pi is always be between 0 and 1. So with a logistic regression model, the link function, or the way that we're linking pi to the linear predictor, was the logit mathematical function. And so if I look at it in the opposite way, where I just have pi itself there, you could say the inverse link function is using the exponential function of the linear predictor divided by 1 plus the exponential function of the linear predictor. Now, these inverse link functions actually are chosen to be the cumulative distribution functions for particular probability distributions. It's kind of interesting. For those of you then who are not necessarily for sure what a cumulative distribution function is, here is a brief introduction. This is a common topic, for example, in a mathematical statistics course. So if you want to know more about that, you can take a look at my mathematical statistics course notes that I have available on chrismiller.com. So let's let x be a random variable, continuous random variable, with a probability density function of f of x. So x could be could have a normal distribution, and then f of x would be that nice bell curve that we're used to seeing. We're going to be very formal here. We're going to let the observed value of x, a possible observed value of x, be noted by little x. So the cumulative distribution function, which is often denoted now as a capital F of x, is simply the probability that x is less than or equal to little x. So like with the normal distribution example, if let's say instead of using x, I use z, I want the probability z is less than 1.96. This could be equivalently written as capital F of 1.96, which is 0.975. In a mathematical context, when we have a continuous random variable, I would need to use an integral then to find that corresponding probability, which ends up being an area underneath the curve, a curve. Now, if you're not comfortable with the calculus aspect, you can think of x now as a discrete random variable. Maybe x has a binomial distribution to it. And all that the CDF is, capital F of x, is the probability that my random variable x is less than a particular value of x. How do I find that? Well, I add up all those corresponding probabilities for when x is less than or equal to x. So for example, if n was, let's say, equal 5 for a binomial distribution, and little x was, let's say, 2, then my CDF evaluated at 2 will be the probability that x is equal to 0, plus the probability x is equal to 1, plus the probability that x is equal to 2. Notice how I'm accumulating probabilities here. If I had capital F evaluated at 3, I would stick another probability there, and I'm accumulating more probabilities. That's where the name cumulative distribution function comes from, CDF for short. Now let's look at a particular probability distribution known as a logistic probability distribution. This is just like any other probability distribution out there, like a normal, like a t-distribution, like a chi-square distribution. If x has a logistic probability distribution, x is then a continuous random variable. And here's what f of x, little f of x, would look like. This is my probability density function. Just like with other probability distributions, there are particular parameters that control the shape of it. One parameter is referred to as mu with a logistic probability distribution. Another one is often referred to as sigma. One could find the CDF here for our logistic probability distribution. You're not responsible for this. If you're interested, here's the derivation using some nice calculus. And notice the form of the CDF. It's starting to look like something familiar that we've seen before with logistic regression. I have the exponential function, and inside I have some stuff. Then I have that divided by 1 plus the exponential function, evaluated at some stuff. Here's what a plot of the probability density function and the cumulative density function, cumulative distribution function look like for specific cases of mu and sigma. So if we look at the plot on the left, that's my PDF. And we can see it looks like it's symmetric about -2, which is what mu is. And in fact, the expected value of expected value of x here is equal to -2. And in fact, the logistic probability distribution is symmetric about its mean, just like the normal distribution is. Now, what differentiates the normal distribution from the logistic distribution is the logistic distribution is often referred to as having fatter tails, meaning that there's more probability out on the outskirts in comparison to a regular old normal distribution or comparable normal distribution. This is similar to what you would have seen, for example, with a t-distribution in terms of the differences between a t and a standard normal distribution. Now, with this fatter tails, then, is you might expect that the variance is larger for a logistic distribution than it is for a random variable with a normal distribution. And in fact, it is. So we can see here the variance of x is sigma squared times an additional constant, where in a comparable normal distribution, we would just simply have sigma squared there. We can come back up here and take a look at the cumulative distribution function. So what this represents is capital F of x. What we just saw above is plotted on the y-axis. So for example, if I want to find f of -5, I could project up and over, and I have about 0.15 approximately. If I were to go up to -2 here, I could project up and over, and this ends up being right here, 0.5. But we see this kind of a S kind of shape to it that we've kind of seen before. Now, you can look at my code on your own. I'm not going to expect you to do this in our course that shows how these plots are being done. I do want to point out one thing here, or actually two things. In order to get my little f of x, I can use the d-logis function, density logistic distribution. To get a probability with my logistic distribution, in other words, to find capital F of x, I can use the p-logis function. You are required to know that. This p-logis function is what I use to generate this plot here, where I just choose a whole bunch of different values of x for the particular mu and the particular sigma that I chose for this plot. Now, equivalently, for a logistic distribution, we could also look at let's say, a standard logistic distribution, just like a standard normal distribution. How do you find it? In a similar way to what we've done before. And this leads to this particular CDF, as what you see here. Again, look at that mathematical function form. Should look familiar. In fact, this is what we use with logistic regression. Note that I had to pause recording there for a minute or two because I found a typo in my notes, and now I have actually corrected it. So we just saw then the CDF for a logistic distribution. Now if we find the inverse of this function, look what we get here. Z is equal to log of f of z divided by 1 minus f of z. So all I did was I solved for z in there. This has a very similar form to what we've seen before for a logistic regression model. And so what we see here is that the link function for a logistic regression model is actually the inverse CDF of a logistic probability distribution. This is where logistic regression gets its name from using a link function that's the inverse of a CDF for a logistic probability distribution. Now note, this does not, and let me emphasize this, does not mean that I assume my data has some kind of logistic probability distribution to it when I do logistic regression. Rather, all we are doing is using the same mathematical form as what we see with a CDF, an inverse CDF of a logistic probability distribution. That's all. Why do we use that mathematical form? Is because we know that a CDF has to always be between 0 and 1, because CDFs accumulate probabilities. So this table then, next in my notes, helps to compare these 3 different binary regression models. Here's the logistic regression model that we've taken a lot of time discussing, probit, complementary log-log. So the link function for logistic regression, the inverse CDF of a logistic distribution. Probit uses the inverse CDF of a normal distribution, and then a complementary log-log regression model uses actually the inverse CDF, what's called a Gumbel distribution, otherwise known as an extreme value distribution. Then the inverse link function then uses the CDF of a logistic distribution for logistic regression, for probit, standard normal, for complementary log-log, the CDF of a standard Gumbel. So, since I'm working with CDFs, again, that guarantees that pi is always between 0 and 1. How do I estimate these particular models then in R? Well, again, I come to my GLM function. For logistic regression, we've used link equal logit. For probit, link equal probit. And for complementary log-log, use C log-log. Okay. Then the next 3 rows then correspond to some information about why these models are used or not used. Symmetry. Remember early on we said that the logistic regression model is rotationally symmetric of about pi equal 0.5. Probit models are exactly this, are like that as well, but a complementary log-log model is not. And so because of that, this is one reason why complementary log-log regression models are actually used very little. It's hard to justify not having that symmetry property. What about odds ratios? So consider a simple model where I have beta 0 plus beta 1 times x. And the left side I have that link function, let's just call it little g for now, of pi. With a logistic regression model, we found that the odds ratio is not dependent upon x at all. That's great. That really makes the interpretation really easy. But for a probit regression model, unfortunately, the odds ratio is dependent upon x. So if I want to look at the odds ratio for in the place-kicking data set where I just have distance in my model, with a logistic regression model, I can say for every 10-yard decrease of distance, here's my odds ratio. With probit regression models, you have to say, well, my odds ratio for 30 to 20 is this, for 40 to 30 is this, for 35 to 25 is this, where those odds ratios will be different. This is why then probit regression models are used much, much less frequently than logistic regression models. Complementary log-log models also have the same issue. So, how often are these models used? I kind of already said this. Logistic regression models are used everywhere. They're so widely used. Probit regression models, they tend to be used a few places every once in a while. I should say every once in a while, you do see these pop up. And it's hard to justify the use of a complementary log-log regression models, although very often they are taught. And so I used to discuss them much more in the past. Now I don't really feel a need to really discuss complementary log-log regression models because I rarely ever see them used. Same thing with Probit. I don't talk about them as much as I used to when teaching this course because they are used much less frequently than a logistic regression model. Still, I think it's good to at least mention the existence of other binary regression models, so that's why I decided it was worthwhile to take the time to discuss these. So another reason why logistic regression models tend to be used more than probit regression models is that both of them usually give you very similar results in the end, in terms of if you were to look at the estimated probability of success. The only time that they would be different is when pi is, let's say, close to 0 or close to 1. Then if you remember how logistic probability distributions have fatter tails than a standard normal, that's why you will see some differences there. But rarely is being so close to 0, so close to 1 relative to pi extremely important. Give you an example. What happens if you were to estimate both these models? So you can see my placekick.r program for the corresponding code here. This is for the model that has just distance in it for the place kicking data set. And we can see from 20 to 50 yards, the models are essentially saying the same thing about the estimated probability of success. There's very little differences among them. Even for larger distances, if you were to compare the logistic to probit, in a practical context for football, they are not really given much of a difference at all. It really wouldn't be worthwhile to use one or the other. Now, you see here the complementary log-log model is seeing some differences between the other models for larger distances. But you might be wondering, well, is that model fitting the data better? Well, it's really tough to see, similar to what we've discussed before. It's really tough to say because there's very little information out there. We will actually look at this a little bit further later in the course, where we do some former numerical comparisons between these three models and find out logistic regression would be preferred. Here are the actual estimated regression models written out. Now you might be looking at this and say, well, geez, those beta hats that you see there are quite different. These models are quite different. And the answer is actually, and actually they're not. We can see from these plots, generally speaking, these models are not a whole lot different. What makes one think, though, that they might be is because of these beta hats. But by only looking at the beta hats themselves, you're not actually taken into the mathematical function form of these models. And by actually plotting the model, you see that indeed the models are very similar to one another. Okay, and I've already talked about this last note here. Again, logistic regression doesn't mean that we are assuming any of our data has a logistic probability distribution. We're just simply taking advantage of the mathematical form of the inverse CDF for a logistic probability distribution so that we can guarantee that pi is between 0 and 1. That's it. So then that concludes this set of notes on generalized linear models.